Let's go ahead and get started. Brighten up the screen a little bit. All right, so we're in section 3.3, and we talked a little bit about it last time, where I wrote up a bunch of formulas for you guys. Now, and I mentioned to you last time also that the book has 4 formulas written down for you guys, and these are the ones right out of the textbook. Let's see if I can lighten this up a little bit if you guys can see it up there. Okay. It's lighter here, but not quite there. Is that better? All right. Okay. Well, these are the main formulas right here that the book goes over. And they just talk about 4 of them. The reality is, because we have already gone through the chain rule and all the aspects of that particular chain rule, that for every rule that we give you guys, there's the rule, and then there's a chain rule version of it. So the reality is, there are 8 derivative formulas for the stuff we're going to go over today. And I'm going to just highlight it one more time. I went over this last time, but I'm going to do it one more time for you guys. Now, in understanding the importance of every one of these guys, the first one is the derivative of e to the x. That classic exponential function that you played around with so much in your high school Algebra 1, Algebra 2 style classes and stuff. This a function of e to the x that we get the PERT formula from, that we'll talk about in the next section, and so forth and so on. This e to the x, what's so important about this e to the x is it's its own derivative. So the derivative of e to the x is e to the x. This is the only function in the universe, it's its own derivative besides 0. Yes, derivative of 0 is 0, but that's not very exciting. This is that exponential function, e to the x. And the derivative of e to the x is e to the x. However, for every rule, there's the rule, and then there's the chain rule version of that rule. The derivative of e to a function is e to the function times the derivative of the exponent. So it's the same rule. Derivative of e to somebody is e to somebody. But then you've got to do, but if you don't have just an x and an exponent, you've got to do times the derivative of the exponent. If you have a to the x, you were unfortunate enough not to have the famous base e, you got another base, like 3 to the x. Well, fine. Derivative of 3 to the x is going to be 3 to the x times the natural log of 3. You got this adjusting factor for not having the original e in the traditional base. But it's pretty much the same formula. Derivative of a to the x is a to the x. You just have to multiply by the natural log of a. But then, derivative of a to a function is going to be a to that function times that adjusting factor, natural log of a, but then times the derivative of the exponent. Natural log of x. The derivative of natural log of x is 1 over x. However, the derivative of the natural log of something other than x, a function, is going to be 1 over the function times the derivative of the function. Now, a lot of people had calculus before. Their teacher would always tell them that the derivative of the natural log of a function is the derivative of the function over the function. And that's right, and when you clean this up, you get f prime of x over f of x. But I always write it like this, to show you the relationship of this 1 over aspect. Derivative natural log of x is 1 over x. Derivative natural log of a function is 1 over the function times the derivative of the inside, the function. If you got a log base a of x, some other base than e, natural log is base e's, you're going to have to, once again, do the adjusting factor. So the derivative of the log base a of x is going to be 1 over x, but then you've got to do that times 1 over the natural log of a. That just adjusts for the fact that you didn't have an e in the base. And the derivative of a log base a of a function is going to be 1 over the function times 1 over the natural log of a adjusting factor times the derivative of the inside. So you can see the connection between these guys. So let's go and beat to death section 3.3. Again, hopefully you watched the awesome pre-section video of section 3.3 and actually wrote down in your notes some of the classic problems that I did for you guys. And so that's why I do the video, to kind of get you a head start on this material. So let's turn the page, because I did these all on the video. including this one. So we'll pick it up with this one right here. Problem number 7. Problem says f of x is equal to the natural log of x cubed plus 10. Okay? We want to take derivative of this guy. Now what you should notice is 1, there's a natural log, and 2, it's not just x, it is x cubed plus 10. So, what we have here is a natural log of a function. According to our rules, the derivative of the natural log of a function is going to be 1 over the function, 1 over x cubed plus 10, times the derivative of the function, which is 3x squared. You can clean this up if you want to and make it 3x squared divided by x cubed plus 10, but I traditionally leave it like this for that. Remember, every time you take a derivative of a natural log of somebody, you got that 1 over aspect to it. f of x is equal to the natural log of the square root of 4x minus 6 over x plus 1. Well, okay. There's 2 ways to do this problem. There's an easy way and a hard way. Looking at your bright and shiny faces this afternoon, you guys are going to do it the hard way. So I'm going to show you guys what the hard way is, and then I'll go behind you and actually show you how to do it the easy way. So the hard way is just jump in with both feet and start taking derivative here. So here we go. The directions stay, take derivative. So f prime of x is going to be equal to, well, what we have here once again is the derivative of the natural log of a function. So derivative natural log of x is 1 over x. Derivative natural log of a function is going to be 1 over the function. So it is 1 over the square root of 4x minus 6 divided by x plus 1 times the derivative of the inside. Now the inside has a square root on it, and we know I don't do square roots. This is the same thing as 4x minus 6 over x plus 1 to the half a power. Now look at that guy right there and tell me, what rule would you use to take derivative of this thing? Well, there's a quotient with it, but that's not the big rule. What's the big rule? Chain rule. I got this weird quotient thing on the inside, but I got that 1/2 on the outside. This is a chain rule problem. Chain rule. Derivative of the outside, inside stays the same time derivative of the inside. So this would be 1/2 x minus 6 over x plus 1. The inside stays the same, raised to the negative 1/2, times derivative of the outside, inside stays the same, chain rule, times the derivative of the inside. The inside is this 4x minus 6 divided by x plus 1 quotient. So I'm going to use the quotient rule on that one. Quotient rule. Derivative of the top, derivative of 4x minus 6 is 4. Derivative of the top times the bottom, x plus 1. Minus the top, 4x minus 6 times derivative of the bottom. What's derivative of x plus 1 with respect to x? 1. All over the bottom, x plus 1 squared. There's my derivative. Luckily, as we did in chapter 2, when we were first dealing with derivatives, we gave you this awesome directions of take the derivative but don't clean it up. Well, here it is, not cleaned up. But you really should clean this stuff up. So if you clean this thing up, let's see here, negative exponent would put this thing on the bottom, and that would be a square root on the bottom, times that square root on the bottom makes it a 4x minus 6 over x plus 1. Divide by a fraction, invert and multiply. I would distribute this numerator and clean it up a little bit and then get my answer. It's going to be a pain, but you can clean up this guy. But I told you guys this was the hard way. I mean, you had to do 1 over the function times the chain rule times the quotient rule. This thing was nasty. Well, the reason why I did it the hard way, first off, was because I want to show you guys that most people would have screwed this problem up. Okay, because it's very nasty, and it's real easy to make a mistake on something like this. However, fortunately for you guys, there's a big old natural log in front of this thing. And you should never forget, as long as you live, John's fundamental theorem of calculus. John's fundamental theorem of calculus is very simple. It's better to clean up your algebra before your calculus than afterwards. Always clean them up first before you take any derivative, or later on in calculus 2, any antiderivative or anything you've got to do with this thing. Clean it up first. So, the easy way, clean it up. So f of x is equal to the natural log of 4x minus 6 over x plus 1 to the half a power. I went ahead and cleaned up that square root. Now, this is logarithms. We know those log properties. That was a requirement of what, 10th, 11th grade type stuff here. Where do powers get to go with logs? In front. So this would be equal to 1/2 the natural log of that 4x minus 6 over x plus 1. And we're not done cleaning it up yet, because this is division. And according to logarithmic properties, division turns into subtraction. So this is equal to 1/2 times the natural log of 4x minus 6 minus the natural log of x plus 1. And I would clean this up one more time by distributing. So I haven't really done any calculus. I've done all algebra here. And I got f of x equaling 1/2 the natural log of 4x minus 6 minus 1/2 the natural log of x plus 1. Now, take derivative. 1/2's a constant. It holds over. It is still, we're taking the natural log of a function. The derivative that I'm trying to drum into your head is, the derivative of the natural log of a function is 1 over the function times the derivative of the function. So this would be times 1 over 4x minus 6 times the derivative of that function, 4x minus 6. What's your 4x minus 6? Just 4. Minus the constant 1/2 stays there. Once again, we're taking derivative of natural log of a function. Derivative of natural log of a function is going to be 1 over the function x plus 1 times the derivative of the function. Derivative of x plus 1 is 1. All right, now clean it up. Well, I've got 1/2 times a 4. I could actually do that up, make that a 2 up there. So f prime of x would be equal to 2 over 4x minus 6 minus 1 over 2 times x plus 1. And I could distribute. There's lots of things I can do to this thing. I could factor out a 2 out of the denominator and cancel. Well, I could do lots of algebra. But pretty much any one of these guys, this is going to be my answer. The answer is 2 divided by 4x minus 6 minus 1 over 2 times x plus 1. Again, if I want that back of the book look, I could factor out a 2 out of the denominator here, and it gives me with 2x minus 3. That would have canceled. So I would have been left with f prime of x is equal to 1 over 2x minus 3 minus 1 over 2 times x plus 1. This is the utmost cleaned up back of the book look to this thing. And I know what you're thinking. Well, geez, Dr. Taylor, you went up there and did it the hard way up here, and you did it the easy way by doing a lot of algebra and cleaning it up, and then you got this nice looking simple answer. That's right. And you know the truth of the matter is, this thing here and this thing here are exactly the same thing. If you clean this up, you basically, here's the rule of thumb. You can clean it up now or you can clean it up later. Looking at cleaning it up later, negative exponent puts it on the bottom. That's a square root times that square root would be actually combined. Then you invert and multiply. You clean up the numerator, clean up the denominator here, and start canceling a bunch of stuff out. You know what pops up? This thing right here. And this is already a nice cleaned up kind of an answer. So never forget John's fundamental rule of calculus. And also never forget this. Even though log properties can be a royal pain in the butt when we studied them way back when in high school and stuff, the fact of the matter is they can help you out lots when it comes to calculus. Because when I'm taking the natural log of these really crappy functions here, I can bust these guys up. And division turns into subtraction, powers go out front using my log properties. Then I'm just taking the natural log of simple stuff, and derivative of that would be very simple. That's going to be the trick, and it's going to be an important trick we're going to use later. Let's do some more problems. Here's another one. F of x is equal to 5 times the square root of x times e to the 2x. Now this whole chapter, including web work, is going to sit there and do a bunch of combination rules on these guys. So once again, we're going to start practicing our product rules, our chain rule, and our quotient rules, but with these new functions. So I'm going to rewrite this guy. This is f of x is equal to 5 times x to the 1/2, because I don't do square roots, times e to the 2x. So the big question, as always, stop, pause, hesitate, and ask yourself, what's the big picture on this thing? What do I see? I see 5x to the 1/2 times e to the 2x. It's a product. I'm going to use the product rule. Product rule, derivative the first times the second plus the first times derivative the second. Derivative the first. Derivative 5x to the 1/2. You take down the 1/2 times the 5 makes it 5/2 x to subtract 1, negative 1/2. Derivative the first times the second times e to the 2x plus the first 5x to the 1/2 times the derivative of the second. Well, again, drumming the rules into your head that you have memorized by now, the derivative of e to the x is e to the x. However, the derivative of e to anything else, e to a function, is e to that function, but then you got to do times the derivative of the exponent. So what's the derivative of e to the 2x? It's e to the 2x times the derivative of the exponent, which is 2. And again, you can clean this guy up if you're so inclined or told to do so. This would be 5e to the 2x divided by 2 times the square root of x. Negative exponent goes on the bottom. A half a power is the square root on the bottom. Plus, let's see here, 5 times 2 is 10. X to the 1/2 is square root of x times e to the 2x. There's the cleaned up version for the back of the book. Take a look at number 10. F of x is equal to the log base 3 of 5x squared plus 4. Now remember our rules, and this is what I'm trying to drum into your head. The derivative of a log base a of x is 1 over x times 1 over the natural log of a. We got to do the adjusting factor because we're not dealing with natural logs here. But with the derivative of the derivative of log base a of a function is going to be 1 over the function times 1 over the natural log of a for the adjusting factor, but then times the derivative of the inside. So f prime of x would be equal to derivative of log base 3 of 5x squared plus 4 is going to be 1 over 5x squared plus 4 times 1 over the natural log of the original base, which was what? 3, times the derivative of the inside. What's the derivative of 5x squared plus 4? 10x. And there's the answer. Does that make sense? Again, look at the rules and look at the formulas as compared to them. Number 11 is f of x equals 7 raised to the 5x. 7 raised to 5x. It's an exponential function. Again, I'll just write down the rule to remind you. When y equals a to a function, the derivative is going to be a to the function times the adjusting factor natural log of a times the derivative of the exponent. So in our problem, f prime of x is equal to, the derivative of 7 to the 5x is going to be 7 to the 5x times the natural log of the original base, which is what? Original base on the exponent? 7. Times the derivative of the exponent. What's the derivative of 5x? 5. And there's my answer. And I'm following literally this rule right here. Before we move on to the next one, this is such an important section here. And what worries me is that you guys did not go back and do all those video problems and write down those answers. So I'm going to ask you guys a question, straight up. How many of you guys watched the awesome pre-section video before you guys take the quiz? Okay. How many of you guys take notes off of that and put it in your notebook? More than I was anticipating. Good. But still quite a few folks don't. So I want to go over these things very quickly because I want you guys to get real good at taking the derivative of these guys. So I've got, 6 more problems to do. Let's do them. On my mark, get set, go. F of x is equal to 5 log base 7 of x. Okay? That is exactly this formula right here. Since it's 5 is a constant, no one cares about it, constants hold over. We take derivative of log base 7 of x, you got to do 1 over x times 1 over the natural log of the original base, which was 7. And I just cleaned it up to make it 1 over x times natural log of a. Number 2, f of x is equal to 7e to the x plus 5x minus sine of x. On your mark, get set, go. That's going to be 17. Derivative of 17e to the x is 17. What's derivative of e to the x? E to the x plus what's derivative of 5x? 5 minus what's derivative of sine of x? Cosine of x. Here's the one that people cry when I put it on test. And you know I'm going to put it on your next test. Y equals e to the negative 5 tangent of x. Well, it's e to a function. So the derivative of e to a function is e to the function, e to the negative 5 times the tangent of x. But then you got to do times the derivative of the exponent. Negative 5 is a constant, leave it alone. What's the derivative of tangent of x? Things we got to have memorized. Secant squared of x. Y equals e to the negative 5x times cosine of 3x. With that times in the middle is a product rule. Derivative the first times the second plus the first time derivative the second. So my derivative, labeling it as I go, derivative e to the negative 5x, well, derivative e to a function is going to be e to the function, e to the negative 5x times derivative of the exponent. What's derivative of negative 5x? Negative 5. Derivative the first times the second, cosine of 3x, plus the first, e to the negative 5x, times the derivative of the second. What's derivative of cosine of 3x, and what rule do you have to use to take derivative of this guy? Cosine of 3x. It's a chain rule. Take derivative of the outside, inside stays the same time derivative of the inside. What's derivative of cosine? Negative sign, the inside 3x stays the same, then times derivative of the inside, derivative of 3x is 3. There's my answer. F of x is equal to the natural log of x. You've got 1 second to tell me the answer because it's pure memorization. 1 over x. That's a rule we have memorized. Okay? And there was that one more. Hold on, it was on the other page that I chunked up here. Let's see what I did with it. Let's see here. Pages, pages, pages. Ah, here it is. This one here. Last video one. F of x is equal to 3 times x to the 6 times the natural log of 3x squared plus 4. Well, I got 3x to the 6 times natural log of 3x squared plus 4. So that is a product. So we shall use the product rule. Derivative the first times the second plus the first time derivative the second. The first is just 3x to the 6. What's derivative of 3x to the 6? 18x to the 5th. Derivative the first times the second natural log of 3x squared plus 4. Plus the first, 3x to the 6 times derivative the second. Derivative natural log of x is 1 over x. Derivative natural log of a function is 1 over the function times derivative of the function. So derivative natural log of 3x squared plus 4 is 1 over 3x squared plus 4 times the derivative of the x, derivative of the inside, derivative of 3x squared plus 4 is 6x. I mean, don't get me wrong, there's lots of cleaning up you can do. 3 times 6 is 18, x to the 6 times x is x to the 7th, and clean up your numerator, but you've got it right here when you took derivative. All right, so I just want to make sure we covered lots and lots of examples here. Now, the importance of this section. Our goal in Calculus 1 is to take the derivative of any function man has ever created, including the incredibly nasty ones. Here's one. Y equals x raised to the square root of x. I got variables in the base. I got variables in the exponents. I got variables everywhere. And I need to take derivative of this guy. Now, because there's variables in the base and variables in the exponent, I'm going to let you know right now, this is not the answer. Y prime equals the square root of x times x to the square root of x minus 1. Because I see this a lot when you teach calculus. And it took me the longest time to figure out where in the world they're getting that stuff from. Well, they're actually getting it from this. Help me out here. If y equals x cubed, what's the derivative? 3x squared. How'd you do that? What'd you do? You took the exponent and you put him out front, and then you subtracted one, right? And that's all they did here. They took that guy and chunked him out front, and then they subtracted one from him. And, well, that's just wrong. Okay, it just doesn't work like that. Because this only works with x to a power n, and n is a number, not a function here. So this is one of those problems that, now, listen up and listen good. Traditionally on the final exam, they're going to prompt you into telling you what to do. But they shouldn't have to. Anytime you have a variable in the base and a variable in the exponent, you've only got one option, and that is something called logarithmic differentiation. Let me explain, and I'll give you steps with this. Logarithmic differentiation is how you take derivative of really nasty stuff. Because I got a variable in the base and a variable in the exponent, and I can't have variables in both places. There's only one thing in the universe that brings down exponents. What's that? Logarithms. And so what we're going to do here is we're going to quote unquote take the log of both sides, to introduce the logarithm in there so I can separate that exponent from that base. Only logarithms do that. And of course, I will use natural logs. So, with logarithmic differentiation, you want steps? Fine, I'll give you steps. Step 1, take natural log both sides. That gives you the natural log of y is equal to the natural log of x raised to the square root of x. It originally did not have a logarithmic in it, but I really wanted one because of those wonderful log properties. So I gave it to him. What I do to one side, I do to the other. Step 2, clean it up. Clean up means use your log properties. This gives me the natural log of y equals natural log of x to the square root of x. Where do powers get to go? Out front. That'll be the square root of x times the natural log of x. Step 3, take derivative, but you're going to do this implicitly. Because you don't have y equals, you've got the natural log of y equals. So, what you're going to do is take derivative with respect to x of the equation. The natural log of y equals, I don't do square roots, that'll be x to the 1/2 times the natural log of x. Well, remember, from implicit differentiation way back when in chapter 2, when you take derivative of a y, you got to tack on that dy over dx. So, what is the derivative of the natural log of y? The derivative natural log of x is 1 over x. Derivative natural log of y is going to be 1 over y times the derivative of the inside, which is your dy over dx. That is the derivative of natural log of y with respect to x. This equals, here we go. You got to take derivative of x to the 1/2 times natural log of x. What rule would you use to take derivative of x to the 1/2 times natural log of x? What is that? Product rule. Derivative of the first times the second plus the first times derivative of the second. Derivative of the first, derivative of x to the 1/2 is going to be 1/2 x to the negative 1/2. Derivative of the first times the second, natural log of x plus the first x to the 1/2 times the derivative of the second. What's derivative of natural log of x? We got that memorized by now. 1 over x. Step 4. Solve for dy over dx. This is going to give me dy over dx is equal to, how do you solve for dy over dx? Well, we got dy over dx being multiplied by 1 over y. So what am I going to do? I'm going to multiply both sides by y. That cancels and leaves me with bracket 1/2 x to the negative 1/2 times the natural log of x plus x to the 1/2 times 1 over x, all that times y. And then you got step number 5. Replace y with function. For you see, the original problem had an x in it. The original problem was x raised to the square root of x. Well, if the original problem has an x in it and only an x in it, well then the derivative can only have x's in it, not this y thing here. So I'm going to replace y with what it's equal to, the original function, x times raised to the square root of x. So the answer to this problem is dy over dx is equal to 1/2 x to the negative 1/2 times the natural log of x plus x to the 1/2 times 1 over x times y, which was x raised to the square root of x. And there's my derivative. And there are 5 steps of doing logarithmic differentiation. So anytime we have to do logarithmic differentiation. These are the 5 steps I use every time. Step 1, take the natural log of both sides. Step 2, clean it up. Usually brings down exponents, or multiplication turns into addition, division turns into subtraction. Use my log properties. Step 3, I take the derivative implicitly. And what you've got to remember is when you take the derivative of that natural log of y, it is 1 over y times dy over dx. And then I solve for dy over dx by multiplying by y on both sides, and then I replace y with the original function, which will give me the derivative in terms of x. There are 2 reasons to use logarithmic differentiation. The first one is this. Pay attention. Anytime you have a function where you have a variable in the base and a variable in the exponent at the same time, you don't have a choice. You've got to do logarithmic differentiation to find the derivative. That's the only way you can do it. The other time when you use logarithmic differentiation, and lack of a better term, is when they say, they told you so. For example, in this next problem. I got the function y equals 9x plus 4 to the 7th times x cubed minus 5 cubed divided by the square root of 3x minus 1. Now honestly, you should be able to take derivative of this thing, no problems at all right now, if I just said take derivative of it. Here's the problem. If I take derivative of this thing and use traditional methods on derivative, what's the big picture here? How would you take derivative of this thing? What do you see? What's the big picture on this particular problem? What rule would you use? I see a big old divide mark in this thing. This is a quotient rule. Quotient rule. Derivative of the top times the bottom minus the top times derivative of the bottom all to the bottom squared. So the answer is going to be huge, right? Now, focus on the top. What rule would you have to use to take derivative of the top? Product rule, because I got this garbage times this garbage. Great. Wait there yet. Product rule. Derivative of the first times the second plus the first time derivative of the second. That's how I'm going to take derivative of the top. But just to take derivative of the first guy, I got 9x plus 4 to the 7th, and the second guy is x cubed minus 5 cubed. Just take derivative of those guys individually, I got to use the chain rule. Derivative of the outside, inside stays the same time, derivative of the inside. Okay? And also, when I take derivative of the bottom down here, I got to do the same thing because I don't do square roots. That's 3x minus 1 to the half, chain rule. Derivative of the outside, inside stays the same time, derivative of the inside. So, pretty much what I'm telling you is this. When you've done this problem, at the end of the day, the answer is going to be about yay long. Okay? Because it's going to be huge because of all the different rules you have to use this thing. It's not very advantageous. But luckily, in this particular problem, they told you, hey, use logarithmic differentiation to do this because it'll make your life so much nicer and it'll clean up an answer much quicker. So we're going to use logarithmic differentiation. So I'm going to spell out the steps, but I don't write it down again. Step 1. Remember, it says take derivative of both sides. So step 1, because they say take logarithmic differentiation, this will be the natural log of y is equal to the natural log of this 9x plus 4 to the 7th times x cubed minus 5 cubed over 3x minus 1 to the half a power. Because remember, I'm cleaning it up because I don't do square roots. Step 1, take natural log both sides. Step 2, use your logarithmic properties to clean it up. So here comes step 2. The natural log of y would be equal to, now what's my logarithmic rules? Multiplication turns into addition. Division turns into subtraction. When you're being multiplied, you're in the numerator. When you're in the denominator, you're being divided. So this would be equal to the natural log of 9x plus 4 to the 7th plus the natural log of x cubed minus 5 cubed minus, for the division, the natural log of 3x minus 1 to the half a power. Does that make sense? But we're not done cleaning up yet because where do these powers get to go? Out front, which really helps us out with the old chain rule aspect of this thing. So I keep cleaning it up. The natural log of y equals 7 times the natural log of 9x plus 4 plus 3 times the natural log of x cubed minus 5 minus the natural log of, minus 1/2, sorry, lost it, 1/2, the natural log of 3x minus 1. Now, we're ready for calculus. Step 3. Step 3 is take derivative implicitly of both sides. So when I take the derivative with respect to x, what am I going to get when I take derivative of the natural log of y? What was the rule on that? Well, derivative natural log of a function is 1 over function times derivative function. So the derivative natural log of y is going to be 1 over y times dy over dx equals 7's a constant, leave it alone. What's derivative natural log of 9x plus 4? Derivative natural log of x is 1 over x. Derivative natural log of a function is 1 over the function times the derivative of the function. So this will be 1 over 9x plus 4 times the derivative of the inside, which is 9. Plus 3 is a constant, holds over. Derivative natural log of x cubed minus 5 is going to be 1 over x cubed minus 5 times the derivative of the inside, which is 3x squared. Minus 1/2 is a constant, leave it alone. Derivative natural log of 3x minus 1 is going to be 1 over 3x minus 1 times derivative of the inside, which is 3. Of course, I'm going to clean this guy up to get that back of the book look to it. But I'm going to go ahead and solve for dy over dx. So multiply by y on both sides. So this is your step 4. And I get dy over dx is equal to bracket. And I'm going to go ahead and clean it up. What is 7 times 9? How much? Yeah, 63. We should know this from the second grade. 63 divided by 9x plus 4 plus, what's 3 times 3x squared? 9x squared divided by x cubed minus 5 minus 3 divided by 2 times 3x minus 1. All that times y. And then your last step, step number 5, is this. Go back and replace y with the original function. So you get dy over dx is equal to 63 over 9x plus 4 plus 9x squared over x cubed minus 5 minus 3 over 2 times 3x minus 1 times y, and y was the original function. I'll put a bracket around it. It is 9x plus 4 to the 7th times x cubed minus 5 cubed divided by the square root of 3x minus 1. And that is my derivative. And the nice thing about using logarithmic differentiation is it cleans up the answer relatively nicely. If I did the traditional product rule, chain rule, quotient rule, sledgehammer aspect of that problem, this answer is going to be all the way across the page. And then we're going to tell you, clean it up. And people are going to go, oh, and whine and complain and cry because they'll make some careless error somehow. The nice thing about logarithmic differentiation, it gives you a nice little cleaned up package answer on this thing too. Does that make sense? Now, so you can use logarithmic differentiation anytime you want to. But in terms of the world we live in terms of point totals and making A's on tests and stuff, there's going to be 2 directions on logarithmic differentiation. One of them is going to be obvious. When I give you a function where you have a variable in the base and a variable in the exponent at the same time, there's only one way you can take rid of that guy. Use logarithmic differentiation. The other thing is we're going to have to tell you use logarithmic differentiation, and it's going to be some product chain quotient rule combination type thing here that's so nasty and so large you look at it and go, I really don't want to take rid of this thing because it's going to be so big. There's your directions here. Does this make sense? Questions? Section 3.4. Section 3.4 is us starting to go back and do applications of this exponential and logarithmic stuff. So honestly, there's a little bit of calculus in this section, but mostly this section is about word problems that you've seen before in algebra, high school algebra 1, algebra 2. But it's been looked at slightly different now that you know some more stuff. Now, I'm trying to kind of give you guys a clue and a hint in terms of this particular material. The material that we're coming across here with this exponential and logarithmic stuff has a direct correlation into a class called differential equations. You guys don't get to sign up for differential equations until it get you through past Calculus 2. This is a class you take after that, especially mechanical, civil, electrical, mechanical, electrical, and computer engineers will typically take this type of class and stuff. Also, some civil engineering majors will take this class. It has a lot of applications. My EE majors, my electrical engineer majors, they live and die for this particular class because this is that direct correlation to all the stuff that they do, that differential equations. Now, here's the deal. I'm going to give you a quote. A function, better English. The rate of change of a function is proportional to itself. Words. The rate of change of a function is proportional to itself, or proportional to the function, if you will. All right, let me put this in code for you. This is in English, and the hardest part about any math class has never been math. It's always been English. There's 14 different ways to express yourself on a word problem, but you've got to put it down to an equation. This is an equation. Let me show you. The word rate of change. What does the word rate mean to you? Rate of change. You know that because we've been beating that to death since chapter 2, especially in this stuff. What does rate of change mean to you? Slope of the tangent line, which means in calculus speak mean the derivative, right? The rate of change means take a derivative. So the rate of change would be the derivative function that'll be dy over, we'll call it dt because we're doing time element here for independent variables here. But this is my derivative, dy, y is the function, dy over dt is means equal to, proportional means there's some kind of constant of proportionality to itself, and itself is referring to the function, y. dy over dt equals k times y. This is a differential equation. Now, the word differential equation scares a lot of people. Oh my goodness, this is some class you got to take after calculus. Well, no, you actually take it while you're still taking Calc 3 and stuff like that. But it's still, quote unquote, hard. Sounds awful. But we're math people. Don't think too deep in this. What is a differential equation? It's an equation that has a bunch of derivatives in it. dy over dt equals k times y. You're equating the derivative function with the actual original function. That's what's going on here. Now, what they're trying to teach you in this section, now we're going to teach you lots in differential equations, but in this section, there's only one function that's relatively nice that you can see that its first derivative and the original function kind of look alike each other. What's derivative e to the x? E to the x. It's its own derivative. So this is your classic function, even in differential equations, that's going to be the style of answer that you're going to have. Because to equate derivatives, and you're going to give first derivatives and second derivatives and maybe even third derivatives. You're going to do lots of derivatives with the original function equations and stuff. But we got something simple. We got just the first derivative and equating to some constant times the original function. When you look at this, the answer to this function is y is going to be equal to p naught e to the kt. It's going to be the exponential function e to the kt. Where P naught is called the initial amount or population. K that it's proportional to is called the growth constant. And T is typically time. Now, it depends on the problem. Time can be measured in years, months, hours, minutes, seconds, so forth and so on. So anytime they tell you in a problem, the quote, the rate of change of the function is proportional to itself, you know that you're going to be using the famous PE to the KT. And you guys would recognize this probably better from your high school class as the original PERT formula. A equals PERT thing from exponential growth, compounded continuous functions, and things like that. It's based upon this. It's actually the solution to a differential equation. So, in your note, in your pre-section video on this section, I actually did this problem and this problem because it's a little bit of algebra and stuff like that, and I talked a little bit about this. So let's go down here to problem number 3, where we actually have a word problem. Chapter 3.4, yay for you people, is nothing but word problems and how to apply, but they're exponential or logarithmic word problems, and we'll talk about, and I got one of every different type they're going to give you guys on this stuff. So let's read the problem number 3 here. It says this. A bacterial culture initially contains 600 cells and grows at a rate proportional to its size. After 5 hours, the population has increased to 620. Find an expression for the number of bacteria after T hours, and then find the number of bacteria after 7 hours, and you can go answer all the questions and stuff. All right, the first thing I want to focus on is this part right here. All right, let's read the problem. Got to convert English to math. That's the hard part. A bacterial culture initially contains 600 cells. That is your P naught, or P of 0, however you want to write it. That's 600. They're telling you the original amount. It's the second part that clues you in on what the formula is. And the culture grows at a rate proportional to its size. Grows at a rate. That rate means you got d function over dt is proportional k times p. I replace y with p. That's what we're talking about for p for population here. Which tells me those words right there, grows at a rate proportional to its size, is the differential equation dp over dt equals kp, means that your answer p of t equals p naught e to the kt is actually the modeling formula for this guy. I will show you why over here. Proof. All right. If you look at p of t, this is your function, equals p naught e to the kt. Can you take the derivative of this guy? What is dp over dt? What's dp over dt? Now I know k is an arbitrary constant. Don't worry about it. You can do it. P naught is a constant. What do constants do when you take derivative? They hold over. Stay the same. Hold right there. Times, what's derivative e to the kt? Well, derivative e to t, derivative e to the t is going to be e to the t. But anything other than t, t being the variable here, derivative e to a function is going to be e to the function. What's derivative e to the kt? Is going to be e to the kt times the derivative of the exponent. What's derivative of k times t? Just k. E to the k times t is just k being the constant. And you'll notice right here, this p prime, or this dp over dt, is equal to the p naught e to the kt is actually the p function times k, and that actually is my modeling equation. This is the function that solves that modeling equation. That's why we study it. You guys would know it better as the old PERT formula from high school and stuff, but why it shows up in nature naturally and stuff. But once you got the formula, here we go. Find an expression. So I have the expression p of t equals p naught e to the kt, and I got more information. What was p naught? 600. So this gives me p of t equals 600 e to the kt. But there are two constants with this stuff. T is time, that's a variable. P naught is the initial population, that's given to be a constant. The other constant is the growth rate, k. So, here we go. After 5 hours, the population has increased to 620. P of 5 hours equals 620. Okay? You with me so far? So, I'm going to plug in time as 5. So that'll be e to the k times 5. times 600, and that's going to be equal to 620. Does that make sense? What are you going to do? Solve for K. How do I solve for K? This is back to your algebra skills. What's your first move? Divide by 600. So this cancels, and you get 620 over 600. I know it reduces, but I'm going to leave it like that. We're going to go for the calculator. Equals e to the 5k. K times 5. Now what kills off e's so I can solve for that exponent? Take natural log both sides. The natural log and e's cancel. This is going to leave me with the natural log of 620 over 600 is equal to 5k. Now what do you got to do to solve for k? Divide by 5 and go grab your calculator. So k is equal to, and grabbing my handy dandy calculator up here, I get the natural log of 620 divided by 600, close parentheses, divided by 5. And it is, I got 0.006, and I don't round, 0.00655799646. This is my k. Does that make sense? So therefore, what is the answer to the problem? What is my modeling equation? Because you got to get this, because if you don't get this, the rest of these points will never be added to your test grade. So, here we go. P of t equals P naught. What was P naught? 600. E to the k, which is 0.00655799646t. Does that make sense? Did I lose you guys anywhere? Because that is your modeling equation. Now, let's understand what's going on here. Okay? This is the equation that maps out exactly what the bacteria is doing. Now I can go answer any kind of questions they have, but you got to come up with the formula first. So, part B. Find the number of bacteria after 7 hours. What you going to do? Plug in 7. So P of t equals 7 is equal to 600 e to the 0.006557 lost my day, 646 times 7. And I'm going to just stick this on the calculator. You don't need to see that. And when I do that, I'm going to get 600 e times 7. Double check me, but I get 628.1854385, and this would be bacteria. Does that make sense? Questions? Look at the next question. What does it ask you? It asks you to, quote, find the rate of growth after 7 hours. Finally, they asked me a derivative question here, okay? And since so many people decided to walk out on me thinking while I'm giving this lecture, there's a special rule for you guys to print your name on, okay? Print your name and sign your name and pass to everybody. Make sure you sign your name before in the class today. All right. So, let's see, Katrina, she's got a midterm exam that she's got to go take, and so she asked to leave early, and I think people saw her leaving early, and therefore they think that nobody's going to be paying attention to this. Well, they were wrong. So sign this, because if your name is not on this thing, you will be marked absent for today. Okay. All right, so here we go. Rate of growth. When you hear that word rate, what does it mean? Derivative. So, remember, here's my formula. P of t equals 600 e to the 0.00655799646t. So what would P prime of t, or dp over dt be? Well, 600 is a constant, leave it alone. Derivative of e to a function is going to be e to the function, e to the 0.00655799646t times the derivative of the exponent. What is derivative of 0.006557 times t? What's derivative of a constant times t? Just a constant. Times this 0.00655794646. There's my derivative. Okay? So what do they want to do? They want me to find this rate of change after 7. So I'm going to plug 7 into this thing. This will be 600 e to the 0.00655794646 times 7 times 0.00655794646. And if you'll notice, this is the answer I got up here. So all I really got to do is take this answer and multiply it by my rate. Just easier way to do it. And when I do that, I end up getting 4.119617846. And I use all the decimals, so when people watch the video and all this other stuff, and they try to kind of work along with their calculator, they know they're actually doing it right. So I'm trying to give you all the decimals on my calculator. Now, tell me the units. What would your units be? This is why we like the Leibniz notation, because this P prime is the same thing as dP over dt, and that helps me figure out what my units should be. What are my units for this problem? So, and understand, after 7 hours, we got this bacteria petri dish. We got some really interesting anthrax or something or other we're playing with. So we're playing with this stuff, and it's beginning to grow in our petri dish, which means we're making more stuff out of this. What does it mean? After 7 hours, what do we got going on here? How fast is it growing? 4.11 what? Bacteria per hour. Population per time. Does that make sense? So right now, after 7 hours, our little petri dish, these cells are dividing at 4.119 bacteria per hour. Okay? Question D. When will the population reach 4,000? 4,000, we got epidemic. Call the CDC out of Atlanta and have the people in the hazmat suits come out and check us out here. When will we reach 4,000? When is a question of what? Time. So, to when, always pay attention to what you're trying to solve for. The question is time. So I'm going to take my equation, which is your 600 e to the 0.00655794646 t, and I'm going to set it equal to the population of 4,000 bacteria, and I'm going to solve for time. Help me out. What's my first move to solve for t? Very good. T is in the exponent. It's in the exponent of the e, so you got to get the e stuff by himself. So I'm going to divide both sides by 600. This will give me e to the 0.00655794646t is equal to, well, I could reduce some stuff and get, what, 40 over 6. That's great. All right, now what? What kills off that e so I can bring down that exponent? Take natural log of both sides. And the natural log of e cancels, leaving me with 0.00655794646t equals the natural log of 40 over 6. What's my last move to solve for this t? Divide by 0.006557646 on both sides. And I get t equals, let's see what I get. Natural log of d divided by 6. I got 289.2848789 what? Hours. So, what does this mean? 289.28 hours. What do I got? Well, let's see now. How many hours in a day? 24. So if I take this and divide by 24, oh, wrong, bad math here. Hold on, let me go back and what was that? 289.2848789. Divide by 24. Sorry, I hit the wrong button on the calculator. How many days is that? We got 12 days. Now we need hours. So I'm going to subtract 12, and I got a 0.053 of an hour. Of a day. I want to convert days to hours. What am I going to do now? We'll go back and multiply just the decimal part by 24, and what do I got? 1 hour. Now I need to know how many minutes. So subtract off the 1. So this is 0.28 of an hour. How many hours in a day? Multiply by what? You got it. 60. And what's that going to give me? 17. So I got 17 minutes minus the 17 minutes. And now we got to convert it to seconds. The 0.09 of a minute, and to convert that to a second, I multiply that decimal part by 60, and I end up getting what? 5.56 minutes. We'll just call it 5.56 seconds, that is. So in other words, what I've got going on here is the famous clock that you see on the movies and stuff of when will the apocalypse happen? 12 days, 1 hour, 17 minutes, and 6 seconds. Call James Bond and let him go fix it. Okay. Does that make sense? Just to try to get you guys behind the math on this type of stuff. But you can also understand the importance of the math. Like I said, this is a classic CDC kind of a problem. Okay, we're probably playing around with something not so hazmatish in the old biology labs around here, but you never know. There's some fun stuff out there to play with, anthrax and all kinds of good stuff. So there we go. 12 days, 1 hour, 17 minutes, and 6 seconds before the world collapses. Speaking of really cool stuff to play with, let's talk about radioactive material. All right? Radioactive material works the exact same way as population growth, though, except for one thing. Radioactive material decays. So we call this a decay or a decay kind of problem. The difference between the two, notice, it's exactly the same formula, except for one thing. K is going to be a decay constant, and your decay constants are expected to be negative. So your radioactive material has the same type of, it basically decays at a rate proportional to itself, kind of a problem. And the K is going to end up being negative on something like this. So let's take a look at this problem here. The half-life of cesium-137 is 30 years. Suppose we got a 900 milligram sample of this thing. Okay? Find the mass that remains after 2 years. In other words, first thing we got to do is we got to have an expression that maps out mathematically the modeling formula for how much cesium-137 we got. Well, how much did we start out with? We have an initial population or an initial amount of 900 milligrams. Right? Not even a gram of this stuff. We got 9/10 of a gram, if you think about it. 900 milligrams. Okay? So my formula is going to be P of t equals P naught e to the kt. It's the same formula as the formula we had before. But the P naught here would be 900. So I end up getting P of t equals 900 e to the kt. The next thing, just like in the last problem, that we got to do is we have got to solve for K. You got to figure out what your, in this case, decay constant is going to be for whatever material you're playing with. In our case, cesium-137. So, they told me the half-life. The definition of half-life is the amount of time it takes for an initial substance to literally decay in half. The half-life of cesium-137 is 30 years, which means when I put in, because of the word half-life, when time equals 30 years, remember I started out with 900 milligrams, how much will I have after 30 years? What's half of 900? 450 milligrams. It will literally be cut in half. Does that make sense? But that's enough information to plug in here so I can solve for k. So I end up getting, 450 equals 900 e to the k times 30, the half-life number. Go solve for k. What's your first move? Solve for k. Divide by 900, and what a huge surprise. What is 450 divided by 900? 1/2 shows up. Equals e to the 30k. What kills off e? Take the natural log of both sides, so natural log of 1/2 equals the natural log of e to the 30k, and the e and the natural log cancel, leaving me natural log of 1/2 equals 30k, and then to solve for k, I divide by 30. And I'm going to stick this on the calculator. So I've got the natural log of 1/2 divided by, keep getting the wrong button there, natural log of 1/2 divided by 30. And what I want you to focus on is, what's the sign of the k number you got? It's negative, as you would have expected it. So k equals negative 0.023104,906. So my mathematical model is P of t equals P naught, which was 900, e to the k, which is a negative 0.023104,906t. This is your modeling equation. Does that make sense? Now, with this modeling equation, go and answer all the questions. Part B. How much of the sample remains after 150 years? So after 150 years, what have we got? So what am I going to do? Plug in time is 150. This would be 900 e to the negative 0.023104,906 times 150. And I'm just going to stick that on the old calculator. And I end up getting this. 900 e times 150. Check me out, but I got 28.125. But this is word problem, physics style problems. Got to have units. What are my units? This is the amount of cesium-137. What was that stuff measured in? Milligrams. Yes?
If you solve for k in terms of years and made the equation in terms of years, and they asked for how much of the sample remains after so many months, would you convert months to years?
Or years to months. It's your choice. Always answer their question. So if you're doing all math in terms of years, and then all of a sudden they want months, take your answer and multiply it times 12. Okay? Does that make sense? You've got to answer their question. So you want to convert it their way to make sure you answer their question. Okay? Because, as you know, both answers are right, but if they ask for it in months, you've got to give it to them in months. But you can still, even though you did all your calculation in years, you can still use all that. Just take your final answer, and all you got to do is convert it over. Kind of like what we did with the days, minutes, hours, seconds, type things. How long, questions? How long after how long will only 4 milligrams remain? How long will it take us to kind of just watch this thing decay down to 4 milligrams? So how long is a question of time. So again, here's my equation, which is P of t equals 900 e to the negative 0.023, 104,906t. 4 milligrams, that goes here. 4 is equal to 900 e to the negative 0.023, 104,906t. Solve for t. How would you solve for t? What's your first move? Got to get the e by himself, so divide by 900. This gives me 4 divided by 900 is equal to e to the negative 0.023, 104,906t. What's my next move? Natural log, both sides. And natural log and e's cancel, leaving me with a natural log of 4 over 900 equals negative 0.023, 104,906t. And then I'm going to divide by negative 0.023, 104,906 on both sides. And I end up getting t equals natural log of 4 divided by 900 divided by that. I got 234.4134357 watt. What's time measured in this problem? Years. And so if they ask me, how many months is that? I take this answer, multiply by 12, and that'll chunk right into web work and be perfectly fine. Does that make sense? Question? Yeah.
Big picture wise, these great decay rates just creating limits.
What? No. Each item that you analyze has their own personal growth or decay rate. Population of Charlotte has a different growth rate than the population of Raleigh. So you're analyzing those particular ones, and those decay rates or growth rates are based upon the information provided on the subject matter. And each subject matter will have its own, but it's not really a limit type thing here. Limit would be something like, as time goes on to infinity, how much material will we have?
I meant if we could extrapolate that from.
Right, but each one is different. And let me give you an example. So you guys, hold on, I got 30 seconds here. I want you guys to focus on, look at the other kind of problems we're going to do. In this particular problem, the next one is Newton's law of cooling. Another awesome differential equation model type thing here. But who uses Newton's law of cooling? Well, lots of people do when you're trying to model all kinds of stuff. But who actually, really fun people actually get to play with this stuff? The coroner. That's right, people who play around with dead bodies. It's great. Okay, understand this. When you come across a crime scene and you're a police officer, what's the first thing they're supposed to do? What's the first thing a police officer is supposed to do? Well, no, they don't put up the yellow tape yet. They call it in, and like you said, they cordon off the area and try to secure the quote-unquote evidence. And they call it in, and immediately, what does the police officer, when the investigators get there, what's the first thing they're supposed to do? If they got a dead body on the scene, they call the coroner, because the coroner has to go and analyze the dead body to quote-unquote figure out when the deed took place. Right? We're going to mathematically show you how the mathematics works behind, basically called Newton's law of cooling, but it's the classic crime scene stuff, CSI type thing here, of why they have to call the coroner first, because immediately they want to start taking measurements of the body to actually figure out when the body was still alive at 98.6 degrees Fahrenheit type thing here. Okay? But here's the deal. Everybody in here, if you happen to meet your demise, is going to decay slightly different from the next person. So each individual will have a different decay constant. That constant is dependent upon the body that you're talking about. And also, we're going to be roasting turkeys on this with the particular example. But don't worry, I'll bring in a dead body problem too. But we're roasting turkeys on this one. Every turkey you go out and buy is going to cook in the oven slightly different from the other types of turkeys and stuff like that. So we're going to mathematically foresee that. Study hard, and I'll see you guys next time. Thank you.